In today's video, we're going to look at section 5.1, which is the start of sets and set theory. So we're just going to do the fundamental things here of looking at the definition of sets and then the definition of some other things like the union and the intersection of these sets that we are going to define. Okay, what is a set? A set is literally just a collection of objects. Okay, so they could be numbers, they could be words, it could be years, it could just be, I don't know, countries, anything that you have. It could be numerical or it could be in words, it doesn't matter. It's just a collection of objects. And each object in that set is called an element. So for example, if I've got the set of numbers, let's say 1 through 5, then the number 3 is just an element in that set. It exists in the set. Whenever we do sets, we tend to write the list of objects in these curly brackets. Okay, so just be aware of that. Whenever you see sets, they will always be in this type of bracket. Another thing to note about sets is that two sets are equal if they contain the same elements as one another. So for example, I could say that 1, 2, 3, 4, 5 is equal to 4, 2, 1, 3, 5. Okay, they're in a different order, but they contain the same elements. You can also say that this set also equals this set. Okay, every element in my first set is in my second set. Now it may occur multiple times in the second set, but it's also true that every single element in my second set occurs in my first set. So they are equal to one another. It doesn't matter how many times each object occurs, each element is in that set. If they contain the exact same elements as one another and each element of one is in the other, it means that you must have equal sets. An example that I want to look at that you're going to see a lot normally through both set theory and in probability is when you toss a coin a certain amount of times and you look at the outcomes that you have. So I'm going to call this set C, and C is just going to be all possible outcomes of tossing a coin 2 times. So C is equal to all possible outcomes of tossing a coin twice. Okay. You can do this 3 times, 4 times. You'll see this as we go through this course. This same set will come up again. But all you have to do is you have to list all possible outcomes for throwing a coin twice. Okay? So let's think about what our outcomes could be. The first time that we toss the coin, we can get heads or tails. Same thing goes with the second time that we toss the coin. We could get heads or tails. So my possible outcomes could be that I get heads followed by heads, or I can still get heads for my first toss and then I can get tails for my second. I could get tails for the first toss and tails for the second toss, or I could get tails and then heads. So that is the list of all possible outcomes. Of course, the more times that you toss the coin, the more outcomes there are going to be. But you've listed all the possible outcomes that you can have from tossing a coin twice. And this tends to be how we write it. So just be aware of that as we go through this course if you do see that again. What I want to do now is to look at the union and intersection of 2 sets. Again, this is a thing that comes up a lot. The union of 2 sets is just the set of all elements that belongs to either set or both sets. So I'll write this down first. A union B, okay, so this is how we say this, A union B, okay, for two sets A and B is just the set of all elements that belong to set A or set B or both. Okay. We'll do an example of this in a second so that you can see it. A intersect B, okay, so A intersection with B that's just the set of elements that belong to both A and B. So it's any element that lands in A and also lands in B. Okay, so it's kind of the overlap of the two sets, which we'll see when we do Venn diagrams. Okay, we'll do a quick example of this so that you can see exactly how this works. So let's say that the set A is going to be 1, 2, 3, 4 and 5, and the set B, I'm going to say is 1, 3, 5, 7, 9, 11. A union B is anything that lands in either set or both, okay? So as long as you find an element that exists in either one of these sets, it's in A union B. So 1, it's actually in A and B. So that's going to be in the union. 2, that exists in A, so that's going to be in A union B. It only has to exist in one of the sets. If it exists in both, great, but it doesn't have to for the union. As long as it exists in one of the sets, it's in the union. 3, 4, 5, 7, 9, and 11. And that's the list of all elements that occur in either A or they occur in B, or some of them, as we see here, 1, 3, and 5, actually occur in both sets. But as long as they exist in one of them, they're in that union. Then A intersect B is any element that occurs in both of the sets. So we see that 1, 3, and 5 are the only elements that occur in both A and B. So A intersection B is just going to be those entries that occur in both of those sets. The next thing that we want to be aware of is the subset of a set. Again, this is going to come up a lot, exactly like the union and intersection are. The subset of a set, and we tend to write it with a special symbol. So let's say B is a subset of a set A, and we write that as B with this symbol, okay? B would be a subset of A. It's kind of like a C with like an extended C with a line underneath it. B is a subset of A if every element of B is an element of A. So it's almost like B is contained inside A. Now those sets can be equal, okay? That's why there is this line underneath. That can mean that B equals A. They can have the exact same elements, but B cannot have any extra elements that don't exist in A. So B is contained in A, whether it's a smaller set or equal to it. Okay, so quick example of this. We'll go back to saying A is equal to 1, 2, 3, 4, 5. Okay. Then I'll do an example here of 1, 3, 3, 4. Okay. In this case, B is a subset of A because every element of B can be found in A. It's just a smaller set. Now again, 3 occurs twice. That's fine, that doesn't matter. But every element of B is also an element of A. A set that we have to consider is, and there's two names for it, it's called the empty set or the null set. Okay. It can be called either one of these. That particular set, we tend to denote it as either a circle with a line through it, or just those set brackets, those curly set brackets with nothing in it. Okay, kind of leads me to what this empty set is. It's just a set that has no elements whatsoever. It's just a set that doesn't contain any elements. It's a subset of every single set. Because it doesn't actually contain any elements, I can say that that empty set exists in every other set. Because it doesn't contain any elements, I don't have to really worry about if it's got any elements that are also existing in another set. So we always say that the empty set is a subset of every set A. So always remember that whenever they say to you, here is a set, now list some subsets of it, you could always say the empty set, it is a subset of any set that you have, because every element in it belongs to the set A, okay? There are no elements, so every element of it does belong to the set. Sometimes, like I said, they will ask you to list possible subsets of a set A. So let's say, we'll do a quick example of this. Let's say that you have a set A, which is just the numbers 1, 2, 3, 4. Okay. Let's list some possible subsets of this. I'll do this as a table. So let's say that we've got the number of elements here and then possible subsets here. Okay, let's say I am looking for a subset that has no elements. Well, that's obviously just the empty set. If I'm looking for subsets that have one element, there are 4 possible subsets that we can have here. We can have 1, 2, 3, 4. Every single one of those sets is a subset of A. Okay. Have 2 elements and there's a lot of these, you don't have to do all of them. 1, 2, there's 1, 3, there's 3, 4. Any subset that has 2 elements in it, where you have like 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, etc. Okay, so there's a lot of those. Same goes for any subset that has 3 elements. Again, there are a lot of these. You just pick any 3 elements that are in A and put them together and that will form a subset. And of course, a particular subset of a set is the set itself. Okay, so a subset that contains 4 elements is actually the set A itself. Okay, the set itself is always a subset because it contains every element that is in the set, so it's always a subset. So remember, whenever they ask you to list some subsets, the empty set, the null set, and the set itself are subsets of a particular set. We need to do a quick definition before we can look at the last thing that you can be asked. That is the universal set. The universal set, we call it U, contains all elements that are in the discussion that we are having. So for example, let's say that I have a set of, I don't know, 2, 4, 6, 8. Okay, I've listed some even numbers there. I could say that the universal set could be all even numbers. Okay, and I've taken a subset of the even numbers. I could take just a random list of numbers, 1, 2, 3, 4, 5, and say that the universal set is all real numbers, and I have just taken a few of those real numbers in my discussion. Okay, so the universal set is just all elements that are within the discussion that we are having. Okay, so U, we tend to call it the universal set. Okay, so like I said, an example of this, a major example of this is normally all real numbers. And then we take particular sets out of that. So for example, if I took, like I said, 1, 2, 3, 4, 5, just that set, it is contained within that bigger universal set. Okay. That leads us to the last definition that we need to look at, which is the complement of a set. Okay. The complement of a set we tend to write as A prime for a set A. And it is all elements that are in that bigger universal set that aren't in A. Okay, I'll do a smaller example of this. Let's say that your universal set was the numbers 1 through 10. Okay, and then we took a set A, which was just the numbers 1, 2, 3, 4, 5. Then the complement of A, or A complement, as you'll sometimes hear it called, is just all the other elements that are in that bigger universal set but are not in A. Okay. I'm going to go through a quick example that is actually in the textbook, but it's very useful as you go through your homeworks, etc., as it takes this union, intersection and complement and puts it all together so that you can kind of see some of the things that you may be asked to do for sets. So this is example 4 on page 188. They've said that there is this set EU, which is, they've used letters for this particular example. You have A, B, C, D, E, F and G. And S is going to be the set A, B and C. And T is the set A, C and D. So like we said, sets don't just have to be numbers. Like in our coin example, we had letters that were representing the things that we were doing. So you can have letters, you can have numbers, you can have words, okay, in your set. So for this example, the first thing I'm going to find is what is the complement of S? Well, it's all the elements that are in that universal set U that are not in S. So it would just be D, E, F, and G. Okay. Then the complement of T is all elements that are in that universal set but are not in T. So that would be B, E, F, and G. Okay. Then the next part, we are looking at S intersect T complement. This is where things get slightly more difficult and the kind of problem that you could be asked. So whenever you get these, kind of work from the inside out and look at what you have. So first we have S intersect T. So what does that mean? It's all elements that exist in both S and T. Okay, so where's the overlap in S and T? Well, that would be A and C. So we know that S intersect T is just the elements A and C. I now need the complement of S intersect T. So that would be everything that is in the universal set that is not in S intersect T. So it's all elements of the universal set that are not A and C. So that would be B, D, E, F, and G. Okay. The next one that we have is complement of S intersect complement of T. Okay. So whenever you do this, again, work from the inside out. Look for the complement of S, look for the complement of T, and then deal with that intersection afterwards. So we've already got the complement of S and the complement of T, so we need to see where they overlap. Well, they both contain E, both contain F, and both contain G. So the intersect of the two of those would just be the set E, F, G. And the final part of the problem that we have is the complement of S union the complement of T. Okay, so again, we've got the two sets, S complement and T complement. We need to find their union. So it's all elements that exist in both S complement and T complement. So A doesn't exist in either of them. We do have B in the complement of T. Then we don't have C. We do have D in the complement of S. E exists in both, F exists in both, and G exists in both. So that would be S complement union T complement. That is a very popular question where they will give you these sets and they will ask you for some of these intersections, unions and complements, etc. And you will kind of have to work systematically through them to figure out what the set is. So this is a really popular problem, so I highly recommend you go back through it and make sure that you understand how we have got each of these sets.